Hi everyone, welcome to my YouTube channel ErudiSpace. I am Dr.S. Mohanty, and today we'll discuss about the work done in steady flow processes. So first we'll derive a general expression for work done in a steady flow process, and then we'll derive different expressions for specific processes like constant volume process, constant pressure process, hyperbolic process, polytropic process, etc. So all of us know that for a closed system, the work done is integration of TdV from V1 to V2. But what is the expression for work done when it comes to your steady flow process? That you can derive by applying first principle and by considering the steady flow energy equations. So all of us know that according to the steady flow energy equation, Q12 plus H1 plus V1 square by 2 plus ZZ1 is equal to H2 plus V2 square by 2 plus ZZ2 plus W12. So here Q12 represents the heat given, W12 represents the work obtained, H1 represents the enthalpy, V1 square by 2 represents the kinetic energy, and GZ1 represents the potential energy. All these are specific terms. This is specific enthalpy, this is specific kinetic energy, this is specific potential energy. H2, V2 square by 2, GZ2 are the corresponding values at the exit point. This represents the entry, this the exit. Now, this can also be represented as Q12 plus H1. We can represent this as KE1, specific kinetic energy, plus PE1, specific potential energy, is equal to H2. Similarly, here we can write KE2 plus PE2 plus W12. This represents, we can represent this Q12 minus W12 is equal to H2 minus H1 plus KE2 minus KE1 plus PE2 minus PE1. And if we represent this in differential terms, this will be del Q minus del W is equal to dH plus d of kinetic energy plus d of potential energy. So we can represent this as equation 1. All of us know that the specific enthalpy H is equal to internal energy plus pressure volume product. So this implies dH is equal to du plus EdV plus VdV. Let this be equation 2. And all of us know that the heat added is the sum of change in internal energy plus the work done. Now, del Q is equal to du plus dV. Let it be equation 3. Now, if you substitute dq in equation 2, what we get? We get dh is equal to del q plus vdp. Let it be equation 4. Now, if this value is substituted in equation 1, we get del q minus del w is equal to del q plus vdp plus d of kinetic energy plus d of potential energy. The change in kinetic and potential energy is negligibly small. So these terms may be eliminated. So this implies that del W is equal to minus VdP. So this implies W is equal to minus VdP integration of minus VdP. So this is actually the expression for the work done in a steady flow process. So then we will actually derive the expression for different specific processes applying the first principle. So let us consider the constant volume process. Constant volume process. Constant volume V is taken out of the integration sign. Minus V is from 1 to 2. So this is equal to minus V P2 minus P1. So this is nothing but it has got no meaning. You may simply represent this as P1 minus P2 into V, because V is constant in both the cases. So this is for a constant volume process. Let us consider the constant pressure process. For constant pressure process, dP is equal to U0. So for constant pressure process, W12 integration of minus VdP from 1 to 2 will become 0, because the change in pressure is 0. Next we'll apply this for hyperbolic process, the process where the product of pressure and volume remains constant. Hyperbolic process. So for hyperbolic process, the product of pressure and volume remains constant. Is a constant. So this implies V is equal to P1 V1 by P1. Now, what will be the work done? W12 will be integration minus of VdP from 1 to 2. You substitute it by P1. This is P. P1 V1 by P. And this is your dP from 1 to 2. So this is equal to minus P1 V1 into integration of dP by P from 1 to 2. To get it as minus P1 V1 ln P from 1 to 2. So that is equal to minus P1 V1 ln P2 minus ln P1. This is equal to P1 V1 ln P1 minus ln P2, that is equal to P1 V1 ln P1 by P2. And for hyperbolic process, you can also represent this as P1 V1 ln V2 by V1, because P1 by P2 is equal to V2 by V1. So this is actually the work output for a hyperbolic process. So now we'll actually derive the expression for work done in a polytropic process. So what happens in a polytropic process? That is Pv to the power n is equal to P1 V1 to the power n is equal to P2 V2. So this implies that V to the power n is equal to P1 V1 to the power n divided by P. And this implies V is equal to P1 to the power 1 by n into V1 divided by P to the power 1 by n. Now the work output for a polytropic process is equal to minus, instead of V you put P1 to the power 1 by n into V1 divided by P to the power 1 by n. into dp from 1 to 2. Now p1 to the power 1 by n into v1 being a constant quantity can be taken out of the integration sign. So this becomes p1 to the power 1 by n into v1 into integration of p to the power minus 1 by n dp from 1 to 2. So that is equal to minus p1 to the power 1 by n into v1 into p to the power minus 1 by n plus 1 divided by minus 1 by n plus 1 from 1 to 2. So this is equal to minus p1 to the power 1 by n into v1 divided by this is n minus 1 plus n. This is p2 to the power n minus 1 plus n minus p2 to the power minus 1 plus n by n. So this is equal to minus p1 to the power 1 by n into v1 into n by n minus 1 into p2 to the power n1 minus 1 by n minus p1 into n minus 1 by n. This is equal to p1 to the power 1 by n gamma 1 into n by n minus 1 into p1 to the power n minus 1 by n minus p2 to the power n minus 1 by n. Actually the minus sign which was there is multiplied. So this becomes p1 to the power n minus 1 by n minus p2 to the power n minus 1 by n. So this is equal to n by n minus 1 into this is p1 to the power 1 by n v1 multiplied by p1 to the power n minus 1 by n minus p1 to the power 1 by n into v1 into p2 to the power n minus 1 by n. So this is equal to n by n minus 1 into p1 to the power 1 by n v1 into p1 to the power n minus 1 by n minus p2 to the power 1 by n d2 into p2 to the power n minus 1 by n. So here what we have done, we have substituted p1 to the power 1 by n v1 by p2 to the power 1 by n v2, because all of us know that for a polytropic process P1 V1 to the power n is equal to P2 V2 to the power n. So this implies P1 to the power 1 by n V1 is equal to P2 to the power 1 by n V2. So that we have simply done. So that is equal to n by n minus 1 into P1, n is LCM, 1 plus n minus 1 into V1 minus P2, LCM n, 1 plus n minus 1 into V2. So that is equal to n by n minus 1, this is P1 V1 minus P2 V2. So this is the expression for work done when it comes to your polytropic process. If it becomes an adiabatic process, then you have to follow the same principle. Only thing is that n is to be substituted by gamma. So if it is a reversible adiabatic process or isentropic process, then work done is equal to gamma by gamma minus 1 into this is P1 V1 minus P2 V2 divided by, this is the expression. Already we have done this. This is n by n minus 1 into P1 V1 minus P2 V2. This is gamma by gamma minus 1 into P1 V1 minus P2 V2. So we have discussed in detail the work done in steady flow process. We have derived the expression for the work done, general expression, which is represented as W12 is integration of minus VdP, and all of us know that when it comes to a closed system, then W12 is integration of PdV, but here it is minus of integration of VdP from 1 to 2. Then we have derived the expression for work done in a flow process, when it is a constant volume process, when it is a constant pressure process, when it is a hyperbolic process, when it is a polytropic process, and then for reversible adiabatic or isentropic process. So I sincerely believe that this lecture would be extremely useful in understanding the concept of work done in steady flow process. And if you have any doubt related to this lecture, please do put questions so that I will try to answer. Thank you very much for watching this video. If you have not subscribed to my channel till now, I would request you to subscribe to my channel, and please do share this video with your friends. Hope to see you soon for another lecture in my YouTube channel, ErudiSpace.